Well, hello and welcome to my new track about financial option theory with Mathematica. This is a new track that I start today. This is the first session that we are doing today. I already have a track on data science with Mathematica that I have on YouTube. And this is now a new track, my second track about the use of Mathematica. And in my data science track, the current session is number 12. It's about parallelism in the Mathematica system. See the link that I have at the end. Today we're starting a new one about financial option theory. Okay, I give a rough overview over the track. So today we're starting with an introduction and we are going quickly into stochastic processes and the basics of option pricing. That involves things like stochastic differential equations, the normal distribution, and a couple of other things that we are covering today. Next session will be about the eponymous Black-Scholes PDE, partial differential equation, and its relationship to the heat equation. Then we're looking at American option pricing, then we're looking at volatility. Then I'll be discussing several advanced and state-of-the-art American option pricing methods, present some papers, and discuss their implementations. Again, probably using a lot of parallelism and CUDA in order to have it state-of-the-art and be an industrial strength option pricing method. And I will probably end my track with an introduction to portfolio theory. So today I'll be giving you an introduction and we start then with a simple cash account evolution. It's like a savings account. You put $100 in a savings account and get interest on it. And we start from there. We start from a simple cash account evolution in order to understand several things that are coming afterwards. We then have to make an excursion to the normal distribution. It is essential infrastructure in order to understand pretty much everything about stochastic differential equations, the Wiener process, the Ito process. It is absolutely essential, so I have to make it a dedicated excursion. Then we are looking at stochastic differential equations, the SDEs, and closer at the Wiener process, the Ito process, and then I will end with European call and put pricing. So let's jump right into it. What is a financial option? A financial option is an option that gives the buyer of the option, also called the owner or the holder of the option, the right, but not the obligation to buy or sell an underlying asset or instrument at a specified strike prior to a specified date, which we call the expiration date, sometimes called maturity. Okay, and we have a few flavors of this. There are the call options that give the holder or the buyer the right, but not the obligation to buy something at a specified price for a specific time period. And the put option is a financial instrument that gives the holder or the buyer the right, but not the obligation to sell something at a specified price for a specified time period. And we also have American and European options, and that simply means that a European option can only be exercised at the expiration, not before. And an American option can be exercised any time until the expiration. That's the only difference here, right? We're talking about these two continents, but they really mean a European option can only be exercised at a specific point in time, the expiration, and the American option can be exercised anytime until expiration, on the expiration day or anytime before. Okay, so an immediate consequence we can derive from that is that it's pretty clear that an American option can never be worth less than a European option, because possibly the American option conveys more rights to the buyer of the option, because we're talking about a time span instead of an instant in time. So obviously the American option can never be less. It can be more, and sometimes it is, but not always. Sometimes American options and European options have the same price, because the right to exercise earlier may be worth nothing. Okay, and options can be designed in many fashions, and we'll focus here on the so-called vanilla options. And those are the ones that are traded most frequently at the options exchanges. They're traded by the billions every day at the options exchanges all over the planet. And unless I specifically indicate that we're talking about exotic options, and I will tell that and it won't happen for a while, we're talking about the vanilla options. For the moment, for the time being, until I say differently, think about vanilla options. And that means we have the following payout profile for the option at the expiration date, at the point in time of the expiration. We have a strike price, in this case, say 80, and if the stock price goes above 80, then we have a dollar per dollar payment that we get. That's the payout that we get, and conceivably that can be a profit. It doesn't have to be a profit. It's just a payout, right? Because you paid something for the option. It's not necessarily a profit, but it can be a profit. So if the strike is 80, then we are receiving stock price minus 80 as a payout at the expiration for the call. If we're talking about a put, then we're getting $80 minus the stock price as a payout if the stock price ends up being less than $80, right? Which again can be a profit, but doesn't have to be. We're just talking about the payout profile here. Whether or not it's a profit is a separate question. We're just calling it the payout profile. Okay, so the shaded area indicates the payout, possibly a profit. If at option expiration the stock price is above the strike, the call holder receives S minus K as a payout, otherwise none. That's the zero. And if at expiration of the stock, if at expiration of the option the stock price is below the strike, the put holder receives K minus S as a payout, otherwise none. That's the zero here above 80. All right. So let's jump a little bit into the cash account evolution. That is something that I think I need to explain first so we understand the basics. So I generally recommend that you manage all dynamic processes where this is possible. It's not always possible in chaos theory, but anything that is well behaved, in quotes, in dynamic processes with differential equations. Because this is how you're going to work with this eventually, so I think it's important to get familiar with it immediately right at the beginning. So you deposit P dollars in a cash account. It's called P for principal. So you deposit a principal of, for example, $100 in a cash account. It pays R times 100% of interest per year, and we are compounding it continuously. That means the change in the account value is R times the account value, right? You have $100 there, 5% interest. So, well, over 1 year, you get $5, right? So the change is R times the actual account value, R times P. And we are using an initial value for the account value. And these types of problems in differential equation theory are called initial value problems, because they model an evolution over time, and we prescribe a fixed value at a specific point in time. That makes it an initial value problem. All right, so written as a differential equation, we are saying y prime of t equals r times y of t, right? The change is a constant number times the level or the value, right? This links state and change of state in one equation. And we need an initial value, so at time 0 we start with our principal. Okay, the problem as such is so simple, it's so trivial, we can do it by hand, or we can use dsolve or dsolve value. They just yawn at it in the Mathematica kernel. So we can just use dsolve value, we give it the equation y prime of t equals r times y of t. We give it the initial value, we're interested in y of t. So here we're saying we want y to be a function of time, and the independent variable is t, and we're getting the solution p times e raised to the power of rt. We could have done this on paper. This is probably the simplest differential equation. You probably had this in your undergraduate class, perhaps already in high school. And since version 11.3, we also have the wonderful new function apply sides, which performs symbolic operations to both sides of the equation or inequality, right? We can use apply sides for both. So we can do here what in high school we did with paper and pencil. We just take the equation that is here, and next we say apply sides, and we simply divide by y of t, right? The equation left and right side, we are just dividing by y of t. And this gives us y prime of t divided by y of 2 equals r, right? That's just what we get. Divide this equation by y of t, you get this fraction equals r. Next, let's integrate this expression with respect to t, and we get the logarithm of y of t equals r times t, right? This is a famous integration result, formula, process, or whatever you want to think of it. If you integrate this ratio, you get the logarithm of y of t. And next, all we need to do is exponentiate it, and the e raised to the power of a logarithm cancels out. We get y of t, and on the right hand side we have e raised to the power of rt. This is exactly what we had here when we solved it directly with dsolve or dsolve value. Okay, so as y of 0 is p, we also have y of t now equals the principal times e to the power of rt, because we have e raised to the power of 0 is 1. So we can simply put p in front of it with a multiplication. Okay, so here's a reminder or refresher on continuous compounding. It is a limit process. So assume that you get r as an annual interest rate, and then after 1 year your initial deposit will be larger by a factor of 1 plus r. And here's how we can see that. You have an amount of capital P that you start with, and after 1 year you add p times r, right? The interest rate applied to your principal multiplication. So you increase your capital by a factor of 1 plus r, right? You have $100. After 1 year you get 5% interest, so you get $105. That's your new account value, and this means that you are multiplying your principal with 1.05, right? 1 and 100% for your principal plus your interest rate. So this is a factor of 1 plus r that you multiply with your principal. Okay, next let's increase the frequency of the compounding. How about we don't do this annually, but we do it monthly? But it's still annual interest, right? These 5% are for the whole year. That means we have to divide the interest rate for every month by 12. Because we do it 12 times, but then of course an annual interest rate has to be divided by the number of compounding periods, in this case 12. So as we keep reinvesting the principal with interest after every month, we get this product. We get 1 plus r over 12 for the first month, times 1 plus r over 12 for the second month, and so forth. Or we simply can use this as a formula, r divided by n raised to the power of n, because this here would be 12 factors, right? We do this 12 times. We replace n with 12, because here we're doing monthly, and we get this formula. Well, if we can do it monthly, how about we do it daily? So it's the same formula, but we move n to 365. And if we take this to the limit, then we're getting this limit process here where n goes to infinity, and we can see this is simply e raised to the power of r. So e raised to the interest rate. And this is a famous classical result, and functions has it. If you look at functions, then we can see this result directly here. It's a long established result that we have, that this limit goes to e to the power of the independent variable here. Okay, so a comment r is not limited to the positive numbers, and functions uses z, and that's usually used to denote complex numbers. So this also works in the complex case, and that would also include negative irrationals. And oftentimes in calculus, you need this for minus 1 over n. So we can also see that if we simply change the sign here, we get 1 over e, because e raised to the power of minus 1 is the reciprocal 1 over e. Okay? But next, note that we don't want the compounding to happen for just 1 year. If we keep reinvesting for t years, with t being an irrational number, we get this formula e raised to the rt power, simply because we also multiply with t here in the exponent. So we still just divide by n, r over n, because it's annual interest, but we do it for t years. So we get e to the power of rt. Okay? So with an annual interest of 5%, for example, our compounding factors for 1 year and 10 years are simply e to the r for 1 year and e to the 10 times r for 10 years. And as I mentioned earlier, we'll be dealing a lot with differential processes here in this track. We'll be dealing with stochastic differential equations and analytic evolution processes. So I recommend you start with a differential equation mindset from the very beginning. And when it comes to differential equations, I think for all practical purposes, think of it as being a flow. And in my opinion, stream plot and vector plot are some of the most illuminating functions in the Mathematica system to understand the overall structure of the differential equation system. So especially when you're new to this, I think make it a habit to use stream plot step 1 of your study of the differential system. It basically allows you to visualize the solution, which is an integration process, without ever actually having computed the solution. You already know what the solution looks like, right? Without having understood it yet. But the visualization greatly helps your intuition. You know what a beast you're dealing with, and the geometry tells you already a lot about your underlying problem. So let's use a stream plot here. Let's have a look at a 1-year evolution at 5% and have a 10-year evolution at 5%. And you see that we're beginning to get some curvature here when we have this for longer maturities, right? We start at a factor 1, that's the principle. We multiply with this factor. And when we use 5% at 1 year, you see that the red arrow ends here at 1.05, right? That's just a 5% interest computation for 1 year. And if we are using 10 years, then we end something like 1.6 or something like that, right? 1.65, which is where the red arrow ends up here for 10 years. Okay, so let's show you how this process evolves when we change the interest rate. When we start with 0, then there is no change over time, right? We get 0 interest, well then our money after 3 years is still the money that we started with. But as we raise the interest rate, we are seeing how these curves are getting steeper. We can do an extreme case like 100% interest that leads to an absolutely enormous increase. We can see that after 1 year, the factor is something like 2.7, right? It's E, right? It's the Euler number, and consequently also when we can ask the question, when can we double it? If we have 100% interest, that would be the logarithm of 2, for example. We get 0.69, and that's where we have it here at 0.69. We have the red arrow reaching 2. But that's for 100% interest, which usually, of course, we don't have. But I want you to understand how these dynamics look at as we let the cash account evolution proceed over multiple years, depending on the interest rate. Okay, next I'd like to make the point that the interest rate can also change in a non-differentiable manner with time. It doesn't have to be the constant that we're using here. And as we integrate and differentiate over time, we really don't need the rate to be constant with time. As long as it's time dependent, we have no problem. So the Federal Reserve typically raises and lowers interest rates in 25 basis point increments. So here's a hypothetical interest rate time series. This is not what we're having in actuality. It's a hypothetical rate, but you see that we're always changing it by 25 basis points. And no sweat if we are trying to solve that in the Mathematica system. We get a time-dependent function that we get simply by solving this differential equation. And let's plot it with a principal of $100. And we see that this would be a 10-year evolution that we get. Note that this curve is not a straight line. It may look like this. But these numbers with 25 basis points are not really big, so the change is not really very visible. But if you put a ruler on your screen, you can see it's not a straight line. And as long as the dependence is only a time dependence, we definitely have no problems here. So let's make it wacky. Let's make it a sine curve that we have, and we have no problems integrating it. We're getting a time-dependent solution again. And if we plot it, we still get a solution. And I point out at this point that integration is a smoothing process here. And the preponderance of the sine function in the interest rate is really smoothed out through the integration. We have to make it very wiggly to see that the wiggliness really percolates through the integration in a visible manner. So let's make it absolutely insanely wiggly here, and then we can still see that the wiggliness percolates through to the solution. Okay, so now let's leave this and let's look at the stock price evolution. And reminder, above we used this differential equation, y prime of t equals r times y of t, with an initial condition where we use the principle at the beginning. And instead of a constant interest rate r, let's use a time-dependent and price-dependent drift rate that we call a, sometimes also called appreciation rate. I think that's where a comes from, for the same differential process. So now we divide by t, and the ratio is now a of t and y of t. So the change, the derivative, is a function that depends on t and also the price, and the price itself is time dependent. Okay, and at t0 we have an initial value y0. And equivalently, in a differential form, it looks like this. Then we have dy of t equals a times dt, and a is our deterministic function depending on t and the stock price. Okay, so I want to make a couple of comments on the drift rate itself. So we call a the drift rate or the appreciation rate, and similar to r above, it describes a deterministic time-dependent manner in which the process is driven over time. And of course, we're not pretending that the drift of a stock price could really just depend on time and the stock price at time t. This would include things like company management quality, shareholders, the company or product image, marketing, unemployment level, strength of the economy, exchange rate, interest rate, inflation, political climate, and so forth. Right? So there are many things that would determine our change in the stock price. And even if we tried, then such a model would simply become too complicated, unpredictable, unmanageable, totally unwieldy, and also unquantifiable. So in stochastic differential equations, it's better to model the unknown, the unquantifiable, as random, rather than trying to develop a complicated deterministic modifier. Usually it's easier to quantify randomness than to try to model determinism in the presence of the unknown. And this is how we're getting into stochastic calculus. So What that means, we have to add a component now for randomness, and we're calling it sigma, which itself is time dependent and stock price dependent, but we now have to multiply with another differential, and we use B for Brownian motion, and we are getting into Brownian motion in a moment. Well, not in a moment, in maybe 10 minutes or so. So we add this deterministic factor and we make it random with the differential on the Brownian motion. So our differential equation now is that d of yt is a deterministic appreciation rate or drift rate times the time differential plus a deterministic function times the Brownian motion differential, again with an initial condition. And b of t is what we call the Brownian motion, and db of t is the corresponding differential. Sigma of t and y of t is a given deterministic function. We want to have a deterministic function for our randomness. And formally, we just require that db of t are independent, normally distributed random variables with a zero mean and a standard deviation square root of dt. And that means the variance is dt. Right? The standard deviation is the square root of the variance, and the variance is the square of the standard deviation. So we require it to be normally distributed with a zero mean, and the standard deviation is the square root of the time differential. So this is how we're expecting this for our equation. And this is now called a stochastic differential equation, or more precisely a stochastic ordinary differential equation. And in order to manage them better, we have to do a quick excursion to the normal distribution, the standard normal distribution, and Brownian motion. It's important for us to understand these components. So let's start with the normal distribution. It is probably the most foundational distribution of all. It's so important, and we see that later with the Brownian motion, that you should even memorize some of its basic properties. The normal distribution will be with you for life, no matter what you work as in finance and data science. It's there to stay. The normal distribution is eternal. You and I are not, but the normal distribution is. So let's look at the probability distribution function called PDF, and also the cumulative distribution function of the normal distribution. That means 0, 1. I sometimes make the distinction and call it the standard normal distribution, because if mu and sigma are not 0, 1, then we have a normal distribution but not a standard normal distribution. Okay, so the formula for the PDF is e raised to the power of minus t squared over 2, and then divided by the square root of 2 pi. We need this division as a normalization factor because the PDF needs to have an integral of 1 if we integrate from minus infinity to plus infinity, right? You probably remember this. One of the requirements of a distribution is that the probability distribution function, probability density function, has an integral of 1 if we go from minus infinity to plus infinity. So we need to divide by this normalization factor. And this is really the Gaussian bell curve. You probably heard the name Gaussian bell curve. So we need to have minus the square of the independent variable in the exponent of the exponential function. And the corresponding CDF is expressed as half of the error function of minus t over square root of 2. This is a symbolic representation of the error function, and it's built in Mathematica, and it's called the error function or the complementary error function. Then it's ERFC. Okay, and strictly speaking, it's a standard normal distribution because mean and standard deviation don't have to be 0 and 1. So in the next step, let's look at this a bit closer. We can see in blue here the Gaussian bell curve. You see why this is called the bell curve. And the cumulative distribution function is the orange curve. And we can see a couple of things about this immediately. For example, the blue curve is symmetric around the y-axis. That means the right half has the same area as the left half, but that means then the CDF at 0 is a half, right? Because the whole integral under the blue curve is 1. So in the middle, given that it's symmetric, it has to be a half. And towards infinity, we are converging towards 1. That's what I said. The integral under the blue curve is 1. That's a requirement for the probability density function to be a distribution density. Okay, so we start at minus infinity at 0. We integrate all the way up to 1. So these are PDF and CDF for the standard normal distribution. And let's look at these, how these change when we vary the parameters. You can clearly see that mu, the mean, is sometimes called a location parameter, because as I change mu, I simply shift the curve up and down. So that's why mu is called a location parameter. And the standard deviation sigma is called a shape parameter. You can see why, because as we change sigma, we can go from rather spiky, rather narrow, to very broad and wide. Right? You see this here, that we lower the level of the blue curve as it gets wider, and we can make it more narrow. Then it becomes more peaked or more spiked at the center mu. So that's why it's called a shape parameter. So we have location and shape here. And of course, the standard normal distribution also has higher moments, and I typically look at the first 4 that we have. The first moment is the mean, and the second is called the standard deviation, right? That's the shape parameter. The third one is called the skew, and the fourth moment is called the kurtosis. And let's look at all first 8. Here I'm creating a list of them. I think the higher ones are not so interesting. I think the ones that are interesting are really just the first 4. I don't think people normally go higher than the kurtosis. And you can also clearly see that if we use the standard normal distribution, that means mu is 0 and sigma is 1. We are getting concrete numbers here for these formula. And you can also clearly see that for mu equals 0, all the odd moments are 0, right? You see a 0 at 1, at 3, at 5, at 7. And for all the even moments, they are non-zero and odd, right? We have 1, 3, 15, 105. So these are the standard formulas for the moments. And again, I want to point out that the Mathematica system lets you compute this very easily in both symbolic form and numeric form. You simply asked for them. You just ask for standard deviation, skew, or kurtosis of the distribution that you want with symbolic parameters, not numeric parameters. You see that mu and sigma here have no values. They're blue. If they had values, they would be black. Okay, so it is instructive, I think, to take random samples and then analyze them, comparing them to the symbolic or perfect solution, right? So above we were talking about quantifying randomness, so let's actually do this. Let's walk the talk, and let's actually create random variates using these distributions. So in RS1, I generate 10,000 normal distributions, and for R2, let's use 1,000,000. And we can clearly see when we put this in a histo, where we use bracketing of 20 bins and in the right curve bracketing of 100 bins, we see the Gaussian bell curve again, right? Not a surprise. So we have the histogram that is now based on actual data. You see it's using RS1, and compare it with the PDF of the normal distribution. So this is not based on sampling. The blue curve is not based on sampling. And if we increase to 1,000,000 samples, we instantly see that we can get the same picture but more refined, right? You can see that the yellow area is pretty much the area under the blue curve. If you look very closely, you see some spikes. So this is real. These are actual samples. You see a little bit of a spike above here. You see a little bit white here. So you can clearly see that the yellow area is real and not faked, but it approximates the blue curve extremely closely. Okay, and let's also plot the samples themselves and not just the binned aggregations in these histos. So let's again use 100,000 random numbers, normally distributed random numbers, and we can see that if we plot them on the x-axis, you can see that they are pretty close, pretty dense along the x-axis itself, and then to the upside and downside they peter out. The density decreases as you go up or down, or usually this would be displayed left or right, but I think here it's better to understand if I display it in a horizontal manner. And the right curve is the same as a histo, which you can, I think, interpret as the density of the left curve, right? The numbers go higher when you have more density here, and left to right or up and down, you see how they peter out. Again, the right curve is a Gaussian bell curve that corresponds to the PDF. Okay, so next let's look at how many we have when we use a threshold where we're asking the absolute number of the sample is less than this threshold. Okay, so we have 1, 2, 3 as standard deviations here. These are the red lines. And we're getting these numbers, and I recommend that you memorize them because they're very important for the standard normal distribution. So if we ask for one standard deviation, in this example with real data, we're getting 0.68. Mind you, this is pretty close to 2/3. And if we use 2 standard deviations, we're pretty close to 95%. And for 3, we get 0.99, more than 99%. So let's look at the exact numbers, because they will be a bit different compared to these actual numbers from the random sample. And here I'm showing you in different ways of integration how to compute them. So if you compute them directly as the CDF with the normal distribution, we're getting them as error function expressions. So again, this is the beauty, one of the many beauties of the Mathematica system, that we can clearly see what is the symbolic representation of it. And it's sometimes important to say that it's the error function of 1 over square root of 2. And the complement then, which is 100% minus this number, is the complementary error function of the same number. This is 1 over square root of 2, just like here. And also the numeric numbers. So these are all the same number, but I wanted to show you several ways of integrating these for the CDF. And my main point here that sometimes you can make your integration much simpler when you exploit symmetry. For example, you can take 2 times the computed number when the function is symmetric, and that means you can simply cut your domain in half. So instead of going from minus k to k, you can simply go from 1 to 3, but you have to double the number, right? The Gaussian bell curve is symmetric, as I said, and instead of computing the whole area under it, why not integrate just 1/2 of it and double it? And this is exactly what we can do here, and it makes the integration much simpler, right? Instead of the full range, take just 50% of it and double the integral. And we can also use n-integrate if we're just interested in the numeric solution. In this case, when we use symbolic integrate, then Mathematica uses symbolic integration, and at the end makes it a numeric solution. And if we are using n-integrate first, we are sometimes faster, not always. If it's so trivial like here, then n-integrate is probably the same speed, could even be faster. But if we have a very complicated integrand, then n-integrate is usually much faster. And here we do the same thing. We just go from 0 to k and double the integral. Here as well, 0 to k and double the integral. So you see that all these tables are the same number, and I really recommend you memorize these numbers, or just roughly keep this in mind. One standard deviation is about 2/3, a little bit above 2/3, 2 standard deviations is a little bit more than 95%, and 3 standard deviations is more than 99%, almost 100%. Okay, so how do we interpret this? Well, as I said, 68% of the samples are between -1 and +1 standard deviations. The complement is 100% minus this number equals 32% are outside of this integration interval or the standard deviations. 95-45 of all samples are between -2 and +2 standard deviations, and 99.73 are between -3 and +3 standard deviations, which means 0.26% are outside of these 3 standard deviations. And these are well-known numbers for the practitioner, and I recommend you memorize them. And we're going to use them again several times later today. So, and a side comment, for more on the exploitation of symmetry in integration, please see my 8th session in my Data Science with Mathematica track. The link is at the end. Okay, so next let's look at how close are we with our samples. So we call them P1, 2, 3, and you can see that, well, we have about 3 decimals after the comma, after the period. Correct. Okay, that was 100,000 samples, and we get 3 correct digits. This already doesn't sound too much bang for the buck. We had to put a lot of effort into it, and we get just 3 decimals. So how about we use 1,000,000 samples? So if we do the same type of computation with 1,000,000, we get better results, but, well, not a lot, right? Here we still have only 3, here we have 3, and here we have 4 correct decimals. Already here we have 4. So, well, going to 1,000,000 isn't really much of an improvement. Very, very small, right? If at all. So we can see from this that with 100,000 random samples for the normal distribution, the experimental results are fairly close to the theoretical values, at least 2 zeros after the decimal. But we didn't make much progress by going up to 1,000,000 samples. With 1,000,000 we get a bit closer. Now we have at least 3 zeros after the decimal. But it seems kind of expensive given that we needed 10 times more as random samples. Okay, next I'd like to point out that oftentimes of practical interest are the integration bounds which result in given CDF values. So this is like the opposite question. First we set the bounds and ask, okay, how much percentage do we get? And oftentimes it's the exact opposite. You're asking for, okay, I want to cover 50% as confidence intervals, or I want to have 99% security or something like that. So if you're pre-specifying the percentages and then back out the bounds that we need to use for the integration, then we need to ask the opposite question, and we can simply do this in Mathematica with solve. Instead of integrating, we can now back it out and like backwards integrate or differentiate. How about we try to solve 2 times the integral of the PDF for a given number a, right? See that a is symbolic, it's blue. We're trying to back out an x, and again I double the integral because I'm going from 0 to x and not from minus x to x. So let's do this, and we see that Mathematica had no problems giving us the inverse function. It's square root of 2 times the inverse error function of our parameter, of our symbolic parameter. But this is great because now we can generalize this and use our table. So if we do this, then we can clearly find out if we want to cover 50%, then we need to have 0.67 as our numeric solution in the independent variable. And 2/3 is about 0.96, and 95% is about 1.95, right? So our interpretation is now 50% of our samples are between minus 0.67 and plus 0.67, and 50% are outside. So if we want to cover 2/3, then we have to integrate from minus 0.96 to plus 0.96. 33% are outside. If you want to cover 90%, then we have to integrate from minus 2.57 standard deviations to 2.57. Then 1% is outside. Now, hypothesis testing is usually done on a 5% level. So we're interested in 95%. So we need to go from minus 1.95 to plus 1.95. That leaves 5% outside. All right. And the right column here are familiar numbers for the practitioner. These numbers here. I recommend you keep a note of it. Okay, so that ends my excursion in the normal distribution. We are gonna need it now for the Brownian motion. So the Brownian motion is named after a Scottish botanist, Robert Brown, who first discovered the phenomenon in 1827. And typically in statistics, in stochastics, many body interactions cannot be solved by a model that accounts for every involved particle, I would add deterministically, but can only be handled with probabilistic models. And here is a link for the Brownian motion, and here is a link about Robert Brown. Please have a look at them. That's your homework. And Brownian motion is probably the most important stochastic process of all. It is for random processes what the normal distribution is for random variables. And related to the Brownian motion is the Wiener process. It basically represents the same underlying random motion, but the name Wiener process denotes that the motion was turned into a process, a one-dimensional process. Brownian motion is not limited to one dimension. Brownian motion happens in n dimensions. The origin was the observation of how molecules, how atoms are moving in a random three-dimensional space. But the Wiener process now is one-dimensional, and it's pretty much the same. Wiener process is pretty much the same as one-dimensional Brownian motion. And to get a feel for Brownian motion, we will now simulate Brownian motion with random samples and do more analyses with them. So let's generate a list of many independent, normally distributed random variables. And we define the time horizon of t time units, that can be years, months, or days, and divide the time into k steps and compute dt as the step length. So we take one time unit and we divide into 1,000 subdivisions, so our dt is t over k. And let's generate 1,000 samples. I have shorted the outputs, right? So we have 5 displayed and 995 not displayed. What we really want is that we want them to be normally distributed with a standard deviation of the square root of dt. That's what we said we need earlier. We're not really interested in a 0,1 normal distribution. We're interested in a 0 square root of dt normal distribution. And that means we have to multiply our list with the square root of dt. So again, let's create 1,000 samples. And dB would now be the list of the increments. Remember, we said d of the Brownian motion is the differential that indicates the changes, the random changes. But we want, at the end of the day, we want Brownian motion, right? Not just the changes. We have the changes, but that's not the process. So to construct Brownian motion, we have to accumulate them. And if we accumulate them, then we now have the Brownian motion as changes, and we have really a Wiener process that we have when we accumulate this. It's a process that uses the Brownian motion changes in order to have this a motion where the numbers change. And this is also sometimes called a random walk. This would probably be the preferred name when you're using Markov theory here. And a more efficient way would be to specify the square root of dt in the normal distribution directly. So now let's create again 1,000 samples, but we're not using 1 in the generation of the samples. Let's use the square root of dt in the generation of these normal distributed samples. And let's accumulate. We're getting a different one, a different process here. Okay, and this now represents the trajectory due to the Brownian motion, also called a random walk. And to better understand the dynamics of the Brownian motion, we should analyze many realizations. Let's do the same thing as we did above with the normal distribution, and then compare them with the square root functions and look at some statistical totals to see if we're doing things right or wrong. So first note that the Brownian motion is normally distributed with a mean of 0 and a standard deviation of the square root of t. So if we do things right, we should expect to see that the probability of Brownian motion samples larger than 1 standard deviation times t should be about the 0.6826 that we saw above, and with 2 standard deviations times t, it should be the 0.9545, and with 3 standard deviations times t, our 0.9973 that we saw above. So we should be able to recreate these numbers. Okay, so let's do it. Let's generate 100 random trajectories of Brownian motion, and let's make sure we use 0 as the mean and square root of t as the standard deviation. Okay, let's do it, and let's plot them, and let's look in particular at the square roots, which are now our standard deviations. And we can see that as we start at 0, and we have most of them between 1 and -1 standard deviations, and it's fading out a little bit more for 2 standard deviations and even more for 3 standard deviations. So you can clearly see the standard deviations here as square roots, and you can see how much is inside and how much is becoming less dense as we go further outside. Okay, so let's also compute these probabilities in order to verify these properties that we have seen above. And we get 0.70, that's not too far away, 0.97, not too far away, and we get 0.9996. The numbers seem to be a match. I think we're good with these samples. Keep in mind there's always error to this. We only took 100 samples here, right? If we took more, this would be more and more precise, and we're gonna do this a little bit later. So now that we have established the Brownian motion here, let's advance to the Wiener process. Again, this is really just the one-dimensional process version of the Brownian motion. And the Wiener process is a real-valued continuous time stochastic process named after the American mathematician Norbert Wiener. It's equivalent to the one-dimensional Brownian motion. And here are 2 more links for you to study as your homework. Here's a link for the Wiener process, and here's a link for Norbert Wiener himself. And since version 9 in Mathematica, we have the Wiener process built in. And for us, it is now easier to handle the Wiener process directly than to generate Brownian motion manually with a normal distribution and then accumulate to get a Brownian motion process. So we simply want to be able to specify mu and sigma directly in a Wiener process and eliminate the entire handling of the normal distribution. We don't really want that excursion, and it's in line with the top-level programming, where we tell the system what to do and not how to do it, right? I simply want to be able to say, I want a Wiener process. I don't want to have to generate all these large number of samples, of random number samples, and then create the Brownian motion on my own, or create the Wiener process on my own, right? Top-level programming means telling the system what to do and not how to do it. I don't want to have an implementation myself. So if we do this here, we also get a nice temporal data object. So off we go with the Wiener process. And notice that the head of this expression is a temporal data expression. Okay, and realize that we only needed to specify mu and sigma. In fact, we can even leave them out if they're standard. That means 0 and 1. And random function needs a beginning and an end and a time stepping. So we needed to specify we start at dt. We want to use steps of dt all the way up to t. And remember, dt was 1/1000. But then we're good to go. Then we can proceed. How about a list line plot of this process? And let's do a handful of those so that we can see what we're talking about. But in the next step, let's try to generate the same plots and statistics as above. And here we do the same thing, but now we specify a Wiener process without parameters, means 0, 1. And you see that we get the same picture. Look at the standard deviations in the square root and in the legend. But note that now we have used a Wiener process for this. And let's verify to see if we let's verify if we set up our Wiener process correctly. We should see the same numbers again, but this time using the Wiener process, right? So for the first number, first standard deviation, we get 0.65. And for the next one, 0.93 and 0.9983, right? Again, the same thing. This should be around 2/3. This should be around 95, a bit more than 95. And here we should have 99 point, I believe it was 7 or something like that. Okay, so the numbers look fairly close to the exact ones. Of course, there's error, but keep in mind we only used 100 samples here. Okay, so this looks fairly good. I think we can trust our Wiener process here. Let's advance one step further and come to the stochastic integral, right? This is a key feature in stochastics. The Ito process is absolutely important to know about and to understand and to be able to manage. We can still do better and generalize than the Wiener process. What we really want ideally is to use stochastic processes or handle stochastic differential equations in a way that is similar to calculus. We are familiar with calculus, we know how to do calculus, but we can't really handle the stochastic differential equations yet. And the Ito process is a way, or more specifically the Ito integral, is a way that lets us treat the stochastic differential equations in a way that is similar to calculus. Okay, so we're coming to Ito calculus, named after a Japanese mathematician, Ito. I don't think I can pronounce the first name properly. It extends the methods of calculus to stochastic processes such as Brownian motion, or more generally the semi-martingales. The Brownian motion is a specific example of the semi-martingales. So here's a hyperlink for you to visit about the Ito calculus. And the central concept is the Ito stochastic integral. It's a stochastic generalization of the Riemann-Stieltjes integral that we have in analysis. And it means that the integrands and the integrators are now stochastic processes. But that's the important improvement. We can really deal with integrands and integrators again. And this makes the Ito stochastic integral extremely powerful and applicable in many areas of science and not just in computational finance. So I make a side note, the Ito stochastic integral can, for example, also be used to compute wavelets. And it's used in security theory, it's used in many things, in botany, in computational physics, computational chemistry, definitely not just in computational finance. And the stochastic, or more precisely Ito stochastic integral of a random non-anticipative function is an integral that we have that is an advancement from our Brownian motion, and it is a stochastic process that we can write down as an integral. And note that we have a deterministic function f of w here. It's important to note f of w is deterministic. It is having d of b of w as the differential. We are integrating over db of w. And so again, these are the key points, and I mentioned them again. It's an integral. It's the integrand is a deterministic function, and the differential is the noise in the Brownian motion. db of w was our noise, our random component in the noise at the beginning with respect to a Wiener process. Okay, of written in differential form, the differential of the Ito process is f of t times the differential of b of t. Now, in order to do this properly, I would have to do a couple of technical definitions. I would have to do this properly with a couple of details, but I would like to leave this out. We need to understand that f needs to be a square integrable process, so we cannot just take any chaotic function f. It needs to be at least square integrable. And there's a couple of details that I'm leaving out now. I want to skip over this, but please read those things up on yourself on the E2 Calculus page. I would like to leave this out for now. And for the next steps, we would have to prove several properties of the stochastic integral, and I also skip them here and refer you to the following two books. One from Stojanovic, Computational Financial Mathematics using Mathematica, and another book by Mikosh, Elementary Stochastic Calculus with Finance in View. All right, so you find further details and explanations here. I have to leave them out because they are so detailed, and in essence, they're not important for what we're doing here. What's important for us is that intuitively, the stochastic integral is very similar to Brownian motion. It wanders up and down without partiality. The difference is only in the intensity of the wandering, which can be any random but non-anticipative function of time. It's now important to emphasize another important point. The stochastic integral possesses another important property that we will be using a lot in this track. We didn't have this before, and we are now going to use it a lot in the future. With f, we have an integrable function or process that we can include in our differential processes and that we can handle deterministically. This is important. We would now like to be able to solve a first-order stochastic diffie that has the form f, right? This is our deterministic function times dt, and you see that this now takes the role of our appreciation rate a, or our drift rate a, right? We are now basically replacing the drift rate with the function f, and then we are adding our deterministic function sigma times the Brownian motion differential. So this looks very similar to what we had before, except we are using now f instead of a. It's the very same differential equation, right? But we are now want to deliberately treat f as a deterministic function, and we're gonna manipulate a lot of it in order to understand the deterministic part and the random part of this differential equation. And note the treatment of f in the above equation, which consists of two parts. The first part is the same as in the ODE, right? F times dt. And that means f describes the deterministic movement, just like the drift rate. The second term in differential form is now sigma times differential of the Brownian motion. And we are now treated as a stochastic integral. It expresses the random wandering, and it means in a way that the SDEs combine ODEs and stochastic integrals, because we have a deterministic part and we have a random part. Let me click this right here, the random part. Okay, so important side note, SDEs combine ODEs and stochastic integrals. All right, and the ability to combine a deterministic drift rate with a random Brownian motion in a single integral is extremely powerful. And since version 9, we have the E2 process built in, so we can use it directly now. So let's do it. Let's look at some realizations, this time using a deterministic drift rate in the E2 process that we didn't have before in the Brownian motion or the Wiener process. So let's just define a sinusoidal drift rate, right? We use dy equals y times the deterministic function here. Look at this factor in front of the time differential. This is a deterministic time-dependent function that we have in front of the time differential. And we have a constant number for the function sigma, our deterministic function sigma, in front of the Wiener process. All right, let's do it. Let's plot it, and we see that we have a time evolution that has random noise, a Wiener process as random noise, with a deterministic function for the deterministic part. that means we can, in theory, now go completely crazy. How about a cosine, right? We have the cosine in front of the Wiener process part. I'm sorry, we have the cosine. We have the cosine in front of the deterministic part, and we have again a constant number in front of the Wiener noise. Okay, so if we look at this, we can clearly see we have the noise component that goes up and down, but over time we have a deterministic cosine. And we can let f of t be y of t itself. So this is like saying our deterministic drift is the stock price. So if we do that, we also get a drift that just goes up with the stock price itself. It can also be t times ft. So this would be time times the stock price, right? So now we get something that looks like this, but sharper in the increase and really not much in the random part and the noise. We can push or pull or shift things. You see that we get this type of figure if we shift time by a number, 0.3 in this case, leaving everything the same, again 1/10 times the Wiener noise. We can set f to 0, that means we have no drift. And note that now there's only the random Wiener process at work. So what does that mean? We are basically recreating our Brownian motion or our Wiener process, because dy is really just dw now. So all the change in this is random, right? There is no deterministic part in it. So let's plot this function. You see that in our differential equation here, there's only a Wiener differential. There is no dt, right? So we have no deterministic part in it. So all change is random. So we get this picture again that we had before, and I like to verify these numbers just to see if we made a mistake. So here again we're using the Ito process that comes from the Wiener process, and our numbers seem to be matching. Again, we have these three numbers that we used as verification before. So now let's apply this a little bit after the theoretical introduction. How about we solve a simple stock price SDE with this? So we use our appreciation rate, our drift rate, and this time we also multiply it with the stock price, and we also multiply the stock price in the noise part, in the random part. So we have S of t in both cases. It's a realistic assumption because the drift is larger with the stock price, right? A $1,000 stock has more drift than a $100 stock, and also the noise seems to increase with the stock price, right? If we have random noise around $100 stock, well then these random changes are much larger with a $1,000 stock. This is usually a realistic assumption, not always, but we can probably assume that the drift and the noise increase with the stock price. So this gives us this differential equation here. So now let's fix some values and generate numbers again. Let's generate some process development here. And we can see with the drift rate of 0.3, mind you, this is like 30% interest, right? Not realistic. We see that something that generally moves up here. And yeah, we start at $100 with our initial capital, right? The stock price is $100 now. We used $100 for the savings account at the beginning. Now let's say we invest our $100 in a stock that is worth $100 when we buy it. And we get simply this drift. And next, I also want to eliminate the random part now to explain to you that if we do this, then the drift rate really just represents the interest rate. So the process is really a risk-free cash account evolution. So we are really recreating the cash account evolution that we had at the beginning. right? So if we use 3% interest over 1 year, then we get a number that's a little bit more than 1.03. It should be. If we do continuous compounding on 3%, we get 1.03 and some change. And over 3%, you can see that we have a little bit of a curvature here. We get the number that's a little bit above 1.3, 1.35, something like this. So let's compute it directly. So the interest rate for 1 year at 3% should be 1.03 and a little bit, right? And this is exactly what we see here, where the blue curve ends up a little bit more than 1.03 after 1 year. And if we compute it with a random process, we say 3% interest times y for the deterministic part. There's no dw here, so we eliminate the random part. Then we're getting the same number, right? So here we have computed it as a Wiener process that doesn't really exist, but we have solved an Ito process. This comes as an Ito process without noise. All right, and for 10 years we get 1.35. You see that number here where the blue curve ends after 10 years. And we have recreated it as an Ito process, deterministic 3%, no random noise, we get the same number back. So it seems we have a fairly good equation here. This SDE seems to be doing what we expect. If there's no noise, it's deterministic interest rate compounding. Okay, so we are reaching a point where it's sometimes impossible to always deal with these processes. Normal distribution, random samples, Brownian motion, Wiener process, Ito process. In the future, we're going to be very interested to derive some explicit formula and also to develop some analytic formulas. In the long run, we want to liberate ourselves from the stochastic calculus and start using analytic methods. So, as the stock price movement should be proportional to the price, it's natural to look at the logarithm of the price. So let's do a substitution. Let's use z, which in the future shall mean the logarithm of the stock price. And we can use Ito calculus to develop a couple of very important and powerful formulas now. And I'm skipping over the details for brevity. Please have a look at page 52 in the Stoyanovich for the derivation of the following formula. So if we use z as the logarithm of the stock price, let's define a new differential equation. So the change in z is now a minus half of sigma squared times dt, that's again our deterministic part, plus sigma of the random part, sigma of the change in noise. Okay, and before we continue, I want to make a side note about the logarithmic stock price. When dealing with simple stock price models, we generally have two alternatives. We consider the price as of t or to consider its logarithm. And both use the same sigma, as you can see, but they have different interpretations. In the s of t case, it's the volatility, and in the case of the logarithm of s of t, it's called the diffusion. And the drift of z is not equal to the appreciation rate of s. I think I need to make this comment to be proper and correct. For our derivation, this isn't going to be much in our way. But I think to be technically correct, I need to emphasize this. But this is now our differential equation that we have. And as sigma is a constant number, the SDE for z that has a right-hand side that is dependent of z can now be solved explicitly just by simple stochastic integration. When we simply do this, we're getting our z of t this time. Here it's just a differential, right? Here we have a dz. Let me highlight this, right? Here we have a dz and here we have a z of t. So we can simply do a stochastic integration. And we want to substitute the difference in the Brownian motion terminal values t and 0 and can derive this very useful formula that we can now simply exponentiate, and we now have a stock price formula, right? When we raise z of t to the power of e, we get back our stock price, because that's how it was defined here. Z is the log of S. And we exponentiate the right-hand side and end up with this formula that we have. So this is P, like our principal, our starting value, times this exponential function, where we have the Brownian motion noise in the exponent. And due to the fact that we have B of t up here in the exponent, this may appear useless at first sight, right? Note that everything else here is deterministic. We have a starting value, we let t run over time in a deterministic value, we have a fixed appreciation rate, we have a fixed standard deviation. All this is deterministic, but we still have B of t in it. And what are we going to do with the Brownian motion term? So this may appear useless at first sight because B of t is still in there and is not directly observable, right? We cannot observe B of t in the market, but it's still useful for conclusions that we can derive from this formula, and we're going to do this in a moment. And it can still be sampled with the normal distributions. And keep in mind, after all, B of t is just Brownian motion, right? So if we use this formula not in an analytic way, but we still sample it, then we can still derive useful conclusions. So regarding the first point, a direct consequence is that S of t is larger than 0 for all t, provided that the starting value is also larger than t. So the stock price never reaches 0. And we will see later that this translates directly into not needing boundary conditions for S equals 0 for many PDEs that we're going to look at in future sessions of this track. Further, the formula can be used to construct confidence bounds for the stock price evolution. And as B is distributed with 0 mean and square root of t as standard deviation, the confidence bounds for S of t are now simply this formula. We have plus minus sigma as the factor in front of B square root of t, with B now taking values such as 1 to 3. So in particular, we can now look at the median curve where this simply disappears, right? We have 0 sigma. So it's just this deterministic formula. Note that this is deterministic. I really want to make that distinction between the deterministic part and the random part. So this is our mean. This is an expectation that we have here. And now again, let's use 100 samples to plot this as an Ito process. And when we do this and we start with an initial value of $75 for the initial stock price, right? Y0 is now our initial price. And we use a drift rate of a half, which is a lot, right? You can see how this is all drifting up, which is definitely not realistic. And volatility of 60%, that's fine. And 1 year, you can see this development. And I want to point out now that the magenta curve is not a straight line. This is our median, right? This is what we have here for the median curve. And if you look closely, it's not a straight line. We start here at 75, but we end up above 100. So look, this is not a straight line, and it has a little bit of curvature in it, but not a lot. We would see even less if we used lower numbers for A and sigma, right? These are inflated numbers to make this visible, but you can clearly see that the main random movement work here is between 1 and -1 standard deviations, and things fade out as we get lower or higher in these standard deviations. Okay, 100 samples gives us this curve, and I'm showing you the median and these standard deviations as confidence bounds. So we can clearly see that this formula was not all that useless after all, even though it has B of t in it, and B of t is not directly observable, because we were still able to sample it with an Ito process, and we learned from it that S of t can never reach 0. Now, for the next parts, let's look a bit closer at this expression A minus sigma squared over 2. We have this here in our stock price expression, or here also in our median curve, right? A minus sigma squared over 2 appears constantly in what we're doing here. And if we look at this a bit closer, then we can see that if it's less than 0, and that's equivalent to saying that half the variance is larger than the drift rate, then all confidence curves approach 0 as time increases. We can see that they all go to 0 with increasing time. But that means that the stock price approaches 0 without ever actually reaching 0, right? We've seen this before. But if, on the other hand, A minus sigma squared is larger than 0, that means the drift rate is larger than half the variance, then the stock price increases towards infinity. And we see it simply in this plot where we let go t from 0 to 1. You see that all these confidence bounds go up to infinity. All right, so this is an important thing to note for this expression. We need to compare the drift rate with the variance. That's an important point for us to make at this point. All right, so next let's go into the European options. We didn't do this just for the fun of it. Eventually we want to price some options with it. And let's apply the stock price SDE to European options. So our stock evolution model will be this simple SDE that we had before. Again, we are multiplying the time change with the drift rate times the stock price, and the noise we multiply with sigma times the stock price, and we need an initial value. That means A and sigma are constants. And we now generate 100 random paths, and we do this with Ito processes, and we compute the payoffs for the expiration times. So we'll use a stock price of 75, a strike of 80, 5% interest, and a quarter year until expiration. So it's typical to use K as the strike. Above we used K for the number of subdivisions that we had for our timeline, and now I'm redefining K to be 80. I don't use the time stepping anymore for K. We now make K the strike in line with the normal terminology. So let's make these definitions. A drift rate of a half, which again is unrealistic and high, but I want to make a point. A standard deviation of a half, stock price 75, 5% interest, and a quarter year for the time to expiration. That's 3 months, and a strike of 80. So let's generate 100 samples with an Ito process, and we're using this differential equation here as above. Let's just generate these 100 samples using the Wiener process as our noise. And if we now apply them to our call payoffs, and remember this was stock price minus 80 for the call or 0, and for the puts it was 80 minus the stock price or 0 for the puts. If we compute them now, then we can see that we're getting a lot of zeros because the stock price ends up above or below the strike, and these stock price versus strike differences, right? In the calls it's price minus the strike, and for the puts it's strike minus call price. So what are the mean payoffs now? And we get these numbers. We need to compute this expectation, and the expectation here is simply the mean, and when we do this we're getting these prices. But a drift rate of a half is fairly large, right? Reasonable is to compare it against interest rate, which is more like 5% than 50%. And right now we are nowhere near 5%, right? The interest rates in most countries are very low now. Some of them even have 0 or negative interest rates. So we can see that the mean call payoff is larger than the mean put payoff. This is unnatural, given that our stock price is 75 and it would have to go some $5 up, which we're not requiring for the puts, but we're requiring it for the calls to reach 80. So there should really be more zeros in the call payoffs than the put payoffs, but there are more zeros in the put payoffs than in the call payoffs. If we are looking at this, and yeah, this never fails me when I generate these random numbers, we see that this is a little bit abnormal, which means we were covering those $5 simply by appreciating the stock in an unreasonable rate, 50% appreciation rate. Okay, so it shows that a large drift rate can overcome any disadvantage that a stock price has when it's less than the strike. And again, we're talking about the calls here. The puts, of course, have an extra advantage. So here, more calls end up in the money than puts. If a stock really has such a strong deterministic drift rate, this would indeed be a good model. And when we talk about portfolio theory, at the end of this track, we are trying to find opportunities where we can quantify and use in a practical way any drift rates that we may perceive. So the drift rate A will really have an important role throughout this entire track. That's why I'm putting so much emphasis on it. But if we assume that the stock's drift rate is just the inflation rate, then we get a mean call payoff that is less than the mean put payoff. So let me change this to something like 5%. Let's again generate 100 Ito samples using a Wiener process, compute the call payoffs, compute the put payoffs. And you see there's much more zeros now in the calls than there are non-zeros, and a lot of, and very few zeros in the put payoffs. So what are the means now? We get 5.63 for the calls and we get 10.0 for the puts. This is more in line with our expectations, and we now have 70 cases where the call payoff is not larger than 0. Correspondingly, the other 30 go to the puts. Okay? So now the question arises, what would be a fair price for such an option, right? We want to price these options because we want to buy them and sell them. So what would be a fair price for them before we started the Ito process? Because before that, we probably want to buy these options. And at the end of the process, we presumably want to sell these options. So we need to discount them. We need to look at the fair value before we start the Ito process, which is a stock price evolution process. And a reasonable choice for a price seems to be the present value, also the net present value, and in portfolio theory then it comes to be the capital value. And we compute them simply by discounting them with a negative interest rate, right? So we take the mean call-offs and we multiply with e to the power of minus RT, then we're getting the net present value. So if we do that, we're getting numbers that are slightly different, right? Slightly for small r, big time difference if we use big R. So we get 5.56 here and we get 9.93 here. I'm sorry, I didn't mean to do that. So these are the terminal values that we get, but discounted because we are looking for fair prices. Okay, and if we compare this to the option prices computed with either the built-in option pricing functions, those are the functions that Mathematica has built in, or our own call and put formula that we still have to develop later, we see that we're not too far away, right? It looks perhaps okay at first sight, but there are still differences, right? From 556 to 582 is something like, what is it, 25 cents or so, and from 993 to 982 is what, like 11 cents or so. So these prices are definitely not great, but again, we only used 100 samples here. We only sampled with 100 Ito processes. So that shows that our prices are perhaps reasonable in terms of methodology, but definitely not good. We have too much error in these price differences. So that shows the prices we've computed based on our discounted mean call payouts or discounted mean put payouts look somewhat okayish at the first attempt with 100 paths, but definitely not great. So then the next question arises, can we improve this if we use more samples? So not just 100, but how about 100 times 100 or 10,000? So if we do this, then let's also go to a parallel version, right? We can use more computations in parallel. This machine has 12 physical cores and I have 16 processes, 16 subkernels on this. So let's go to parallel to save some time. Otherwise it would take too long for 10,000 samples, and we are already done here. And we now get 575 for the calls and 982 for the puts. So I think the put price is much better. We already have 2 correct decimals, but the call price is still disappointing. The call price is still 7 cents away. The put price is already 2 decimal points correct. So we're learning that we're slowly getting closer. But this is still not good. And can we still do better? But we realize that we still have to generate all these trajectories. We are still sampling from this SDE. And can we do better? Can we go to an explicit solution, or can we go to an analytic solution? So when we look at this closer, we can develop the explicit solution, and you remember this from the median value, right? Given that we have all these random processes, we should assume that the median price is what is observed in the real life, right? We can always deviate from reality or from what is a good expectation by assuming random coincidences to the upside and to the downside. But for a reasonable model, it's reasonable to take the median. And if we look at this closer, then we can have this explicit formula for a reasonable stock price, but it still contains the random noise component in it. So the rightmost expression here is something that we should work with in the next steps. So let's set the appreciation rate to R again, as we just did before. This still has RA in here. The appreciation rate to the interest rate. And from now on, it makes sense to go backwards in time, because we are interested in the price of the option at the beginning when we're buying it. So we have to go backwards in time because we are looking at the terminal payoffs, right? But that's the end of it. When we want to determine a price, we need to start looking at the beginning of the process. So we go backwards in time, so we use t minus t instead of t, and we set the original principal to the initial stock price. And if we do this, then we get this formula where we now have Ts of capital T on the left-hand side, and we have t minus t in the exponent instead of t, right? Here we used t, or here we used t in this formula. We now have t minus t. And we also have t minus t in the independent argument of the Brownian motion. So that means we can now compute the options price in the following manner. E stands for the expectation, and here we can simply take the mean. When we have so many samples, we can take the simple mean, because the mean here represents the reasonable expectation. In the future, the mean will be, in the future, the expectation will be something else. We will probably use the integral most of the time for this. And these formulas, the exponential is already in front of it. So we are now with this formula where I'm just using the second representation where I have this as a product, right? Here we have sigma b in the exponent, but additive in the exponent to the exponential function. We can make it a product by taking the e to the random part a separate factor here. This makes it easier for the next step. So these two formulas are really the same. I'm just turning this sum here in the exponent to be a product of these two exponential functions. Okay, and if we do that and we use this computed option price as a discounted expectation, then we are getting these results that we can now use to compute 10 million samples. And look how much faster this is, right? These prices come back instantly, even though we use 10 million samples for the call price and 10 million samples for the put price, right? You see these formulas just here. Here are these, here's S0 times the exponential, and then we need to have the exponential again for the noise part, and we map this over the payout profile. We take the mean of it and we discontinue, right? So this is what's happening here with these formulas, and we see that we're getting really close. This is almost 582, and you remember that this was 582,133, and for the put price again 582,611, pretty close to 582,755. So we definitely made a lot of progress here by using 10 million samples. So we're getting much better results here and much faster. This uses 10 million samples, but the big advantage is, as I mentioned earlier, not for this trajectory creation. We didn't create this whole path, this entire Wiener or Ito process, but we really were able to consume one of these samples for each option price. This is the result of 10 million calls and 10 million puts. Before, we just were able to create 100 trajectories, and we used all these random samples as increments of the overall process that we used. This is because the Wiener or Ito processes are much slower to compute. They're much more complex, and we use these changes as the changes in these processes, right? We really needed just normally distributed samples per option and not to generate all these whole trajectories. So we are changing from a path to a point. And that also means we're back to the standard normal distribution for performance reasons, right? Remember, the standard normal distribution is gonna be with us for life. So we're back to this normal distribution, but now simply for performance reasons, because it's so much faster to just use the normal distribution here to generate direct our samples. Now, a footnote, to be fair, we didn't have to use 1,000 time steps in the Ito process, right? Remember, our dt was 1/1000. And that is true, we didn't have to use 1/1000 for dt, but at the same time, if we use larger values for dt, then we lose precision again, right? We don't want to have large time steps, then we're losing overall precision for this. We should really have a pretty dense process. And even though we now did it this way, we used the random samples or Monte-Carlo approach directly per option and not to create trajectories, we can see that this process is still quite inefficient. We needed 10 million samples to get about 2 correct decimals of the option price. And I think that's pretty terrible, right? We can clearly see that we need to start using analytic methods. Monte-Carlo is not great. 2 decimals for 10 million samples, that's not a lot of bang for the buck, right? It's rather little bang for a lot of buck. So we should try to improve these methods. Monte-Carlo is definitely not a great approach to this. These 10 million samples give us only 2 correct decimals. Yeah, we've seen this already before, or just take the difference here. We see that we have 2 zeros after the decimal. So the next question could be, how about 100 million then, right? So let's parallelize this even further, and let's use 100 million samples each. And this computation will again take a while, but unfortunately we now only get 3 correct decimals for 100 million samples, right? It's increasingly inefficient. You see in the difference here 3 zeros after the comma and 3 zeros after the comma for the puts, right? And at the large cost, the compute time and memory storage. So also let's look at memory, right? We should consider cost in multiple dimensions. Cost can be currency, like US dollar. Cost can be memory consumption, and cost can be time. So let's accept these 3 dimensions of cost, and let's say compute time is a cost and memory storage is a time. So let's look at the byte count for 100 million random samples, and it's 800 million. It's over 800 million in the byte count for 100 million random samples. So that's a lot of buck that we need to input in order to get some bang. And it's definitely not good. We only get 3 correct decimals, as we've seen up here. So to take this to an extreme, to go to the next step, how about we try to get 7 or 8 correct digits? And for that, I will need to use a billion samples. There's just no way around that. And in order to go to a billion samples, I now have to switch my computation method to CUDA, and I need to compile the computation of the payout profiles. Otherwise, we are sitting here until Christmas or something like that. So let's load the CUDA package, and let's set my CUDA device to device number 2. There's a reason for that. You can here see the output of NVIDIA-SMI. I have a GTX 980 that's not state-of-the-art anymore today, and that is only 4 GB memory. But it's still the fastest card. But for a billion samples now, I need some 7.7 GB of memory. And I have 4 GPUs on Tesla K80 cards. You can see here that I have 12 GB available. So that's the reason I picked my second GPU. It's GPU 1, and in Mathematica speak that would make it CUDA device 2. So now let's keep this on top. And after I've defined my CUDA device 2, let's load the random CUDA program from the samples. So we have a lot of sample files that were provided by NVIDIA and Wolfram Research. So let's load this function, and there is a bug in the package for the Linux version, so we have to load this package twice, but then it works. And before I now generate these samples, I want you to take a look at this number here. There are already 11 megabytes in it. When I run this, I want you to see that this goes up to 7.7 gigabytes, right? Just for a billion samples, we need 7.7 gigabytes here. You will see that the utilization also goes up to something like 12 to 24%. But the important number is this one here, and you will also see that the power usage will zoom up from 28 watts to something like 50 watts, okay? Just because we have a billion samples and want to compute these billion random normally distributed samples. So here we define we want a billion samples, and we need to allocate this memory. Then we call the function to compute these things in the CUDA memory, in the GPU memory, and then we have to use mem copies in order to get the data from the GPU on the host. So let's now trigger the computation. So when I submit this, please have a look that this zooms up to 7.7 gigabytes instantly. That is the memory allocate. We now have the computation here, 12% for the generation for the random samples. Now we're done with that, but note that the cell bracket is still highlighted, so it's still doing something, and those are the mem copies. We now need to get the data back from the GPU to the host. Okay, we're done with CUDA, and we now have these samples in RV. And next I want to compile the computation of the call input payout profiles. And I point out specifically that it's really cool that in Mathematica we can use C compilation. Directly in your compile, we can say compilation target goes to C, and now we are really compiling into machine code. That makes the computation significantly faster. Okay, so now let's use these functions. Let's look at the results for the call payout profile for a billion numbers and the put payout profile result for a billion numbers, and compute the difference. So this will take a few seconds, but it's also for a billion numbers. But you see that after a few seconds we're actually done, because we did compile it into machine code with this compiler option. So this is a major improvement. If we didn't compile this, then this would take an enormous amount of time for a billion samples. So let's use machine code for this. And then let's do the comparison. The call results are already there, 582. Well, that's the number we remember. And here are the puts, 9.82755. Right? Those are these 5 digits that we remember. And the difference shows us that we're correct to 7 or 8 digits. Here with 7, 8 correct digits, that's great, but we also needed a billion samples for that, and that's very inefficient. let's look at the table, the difference comparison for 10 million, 100 million, and 1 billion, right? Here we have 2 correct decimals, and we still have 2 here for 100 million samples, and we needed 1 billion samples to get 7 to 8 digits correct, right? So you can see that Monte-Carlo sampling, that it's a method that definitely works. We're getting the very same prices. I mean, at the same time, it also proves that the computations are totally correct, because we are getting 7 or 8 correct digits here. But it should always be the method of last resort. We needed 100 million samples to get 3 correct decimals. We needed 1 billion samples to get 7 to 8 correct decimals. And it consumed about 7.7 gigabytes of memory on the GPU. And it still took us a few seconds even for the compiled version of the payout profile computations. And I mean, to be fair, about half of that time is mem copies on the GPU. But still, it's a very expensive process to do this. And here, let's look at the memory information on the GPU, right? 1 million numbers. And again, we have a byte count of 8 billion, right? This is rather expensive. A lot of buck for the bang. So here is my summary, somewhat of a heads up for this. Unfortunately, Monte-Carlo is the only choice for some of the most complicated financial derivatives, not the standard options we're talking about here. And some financial derivatives, they're oftentimes called exotics, are so complicated that analytic methods for them are not available. And that's another reason, I think, to start looking at GPU-based massively parallel computing. And that's the method that most market makers have already been doing for years. And I'm pointing out that CUDA is really not all that hard. And as you watch this class, you probably know already some C. So it shouldn't be too hard for you to learn CUDA and program it. But definitely make Monte-Carlo the method of last resort. It's if it's the only choice, then certainly use it, but use it only if it is your only choice. Okay? But speaking about CUDA, now that we're having it, let's compare the explicit prices that NVIDIA has put into their sample codes, because we also have Black-Scholes, a CUDA kernel, in the support files. So let's load that, and let's define a function for that with CUDA function load so that we can use it in Mathematica. And let's compute 64 options. We're going from 60 in steps of a half all the way to the upper limit. What was it? Something like 85 or so. So we allocate memory. We can even do it as floats. That's more memory efficient. We may have problems with the precision, but for these simple samples, it doesn't show for a couple of decimals. And in the real market, these option prices are rounded to 2 decimals. So float is definitely okay here. We want to have an 80 strike. We want to have a time to expiration of 3 months. The risk-free rate of interest is still 5%, and we use the volatility of 50%. So let's make these definitions. I won't show you the SMI output because it's so fast. Let's just compute these numbers, and we now have it in CUDA memory. We can get it with CUDA memory get, and here is our options prices, and we find our prices back at the 75 strike, right? The 582,133 for the calls and 982,755 familiar numbers that we had computed earlier. So this is what a trading screen looks like. An option trading screen has the calls in a left column, the strikes in the middle, and the puts in a column to the right of the strikes, right? These are the 3 center columns of an options trading screen. Then there are more columns going out to the side, to the left and to the right. There are more diagnostics, more derived numbers for the calls to the left, and more to the right for the puts. Usually those are then called the Greeks. You would then get numbers like delta, gamma, theta, vega, kappa, and so forth. All right, but these are the three center columns in a professional options trading screen with the strike in the middle, and here are our prices. So we are in this lucky position that we have Black-Scholes code. Think of this as European prices, right? We say Black-Scholes here. What this means, I think the name is a misnomer. It really means European options, and that's what we've computed in today's session. We didn't look at American prices yet. But what sometimes is done, which I think is unfortunate, is that people say European options are Black-Scholes and American options then are called Americans or trees or whatever else. So when it says Black-Scholes here in the samples, just think European options. And this is what we have computed here. All right, quick peek at the memory situation. So we computed for 64. We computed for 64 options. That's a byte count of 256, and the same for the puts. All right, and when you're done, you should always unload the memory to make it available again. You can see the memory is now back to 68. That's the function that we have loaded into memory, but no data for it. Okay, so for the practitioner, these prices are almost worthless because they are European prices and not American prices. And European options trade very little in the options markets. Sometimes they do. A few things are European prices, mostly stock indices that has a dividend reasons. But for most practical purposes, all the options trade as American options. And we're going to do this later. For now, we just wanted to verify if our foundations, our basic math, statistics on the SDEs and European pricing are correct. Okay, I want to give a critical view and a discussion of the log returns assumptions and maybe talk about alternatives. It's a fair question to ask, is this really realistic that we take the logarithm of the stock prices? Are there alternatives? And what about the distributional assumptions that we have? So let's compare the normal distribution with the student t distribution. The student t has real expectations when nu is larger than 1, and also a real standard deviation when nu is larger than 2. Nu is the tail exponent of the distribution, and since the recovery from the Great Recession, the student t fit for the log returns has been absolutely great, absolutely excellent. So let's look at some of these properties. Let's look at the first four moments. That's the mean, the standard deviation, the skew, and the kurtosis. And these are pretty much standard parameters. We have mu again as the mean. We have a standard deviation here that involves a square root and a fraction. So we need to say that we need to have nu larger than 0 for this square root to be a real number. And we have a skew of 0 if nu is larger than 3 and a kurtosis. All right, so let's assume a student t distribution for Amazon. And one of the great features of the Mathematica system is that you have a lot of financial time series already built in. All you need to do is query it with financial data, say your instrument, time period, or points in time, and you get the data back. So in P data, I now have the Amazon stock price series since the beginning of 2014. Now let's take consecutive differences. The function differences will compute you consecutive differences. We take the log of the second column, and let's do 1000 bin histo in PDF form. So we see this looks like somewhat symmetrically distributed around 0. And we can now also create an estimated distribution pretty easy in Mathematica. We use the function estimated distribution. We do this on our data, and we we prescribe the student t distribution with mu, sigma, nu as the 3 parameters. Note again, I'm not providing numbers here. These are blue. So these are just unevaluated formal parameters. And the return is a student t distribution expression with these 3 parameters evaluated for the data we provided in LR. And for the next plots, we also need a smooth kernel distribution on LR, and we need an empirical distribution on LR. And now we are ready to compare these. And if we look at these, then we see that we have a fit here that doesn't quite match. It somewhat captures in the orange curve what we have in the blue curve, but we can't really call it a great fit. And when we look at the tail fit plot, we see that it's also pretty bad. The green curve is substantially below the blue curve. And as we get into the tails, things get a little bit flaky. All right, you see that this is not exactly a great fit. We see that the fit isn't quite right, and not only in the tails, but we also see that that green is different from blue around 0. So that was the student T. So the question is, would the standard normal distribution be a better one? Would the standard distribution, which is the foundation for standard option pricing, Black-Scholes, right, and Wiener process and Brownian motion, Ito, what we talked about earlier, would this be better? So let's look at it. And if we do this, then we're getting surprised because the fit in the standard normal distribution seems to be even worse, and the tail fit seems to be just atrocious, right? There's just too much difference here. So it seems the fit with the standard normal distribution is pretty terrible. Yet it's the standard foundation for all the smart money options trading that happens at the options exchanges. So as a next step, we can do hypothesis testing, right? So let's create an estimated distribution with the normal distribution. Again, in blue, we use mu and sigma. That means we don't provide numbers for these. We want them to be evaluated. Blue means that the expression is unevaluated. And then we can ask the question about a distribution fit test, right? We want to do a hypothesis testing. So we use the function distribution fit test on our actual data, the estimated distribution that we want to test against, and we are requesting the hypothesis test data. And this returns us an HT, in this case I called it HT, but that returns us a distribution fit test object, and we know we can query it for test data table and test conclusion. And we want this for all the tests that are available. In this case, it's 12 for the normal distribution. And we see that all the p-values are 0. And with test conclusion, we even get a full natural language sentence that tells us what is going on with that test. So let's just take the first one, Anders and Darling. We get the null hypothesis that the data is distributed according to the normal distribution with these parameters is rejected at the 5% level. And we get the same message for all of them. And so I just was lazy and I put all of these tests together, made them one big string, and then counted the word rejected in them and divided by 12. So we get 100% of the tests. These 12s are rejecting it. Okay. So that means the student T gives us a better fit than the normal distribution. But we can't use it either because it is unfortunately incompatible with the stochastic calculus or the Ito foundations that we've developed earlier. So let's show this as well. Let's generate 10,000 random variates for the student T and 1,000 for the normal distribution. And we see that the student T is pretty jumpy and that it takes a while for convergence. And we see this especially when we do this a couple of times. Here, look at this big jump. We have a lot of discontinuities here, and it takes a long time until we get convergence. And the normal distribution, we don't have so many jumps and we get much better convergence. So let's take a few samples here and we get the wackiest forms and shapes for the student T. We get these jumps, we get a lot of discontinuities, and overall we see that this is simply not in line with the Ito calculus assumptions that we have made. The student T is too jumpy, the convergence over time happens too slow, and I think we see this by comparing 10,000 student T samples against 1,000 normal samples, right? The normal converges much faster. So we get strong discontinuous jumps in the standard deviation of the student T, and we see that the Pareto tail is 3, that means greater than 2. And in this case, it will eventually converge, but there will be discontinuous jumps early in the series. You see these jumps here, and convergence happens much later. So these jumps suggest that stochastic calculus, with the assumption that the standard deviation converges rapidly, is simply not true in the case of the student T. The normal disk converges quickly, but it provides for a bad fit, as we've seen. And even that may not be good enough for option maturities less than a few months. You see these points here that are jumping around. But the option maturities, the option expirations that trade the most frequently are the short-term options, right? The long-term options do not trade as frequently, as fast as the short-term options. So this is a bit of a dilemma, right? We get better fits with the student T, but it's incompatible with our theoretical assumptions. And the standard normal converges faster, but it gives us a bad fit, and we still get jumpiness here for shorter times to expiration. Okay, you may say Amazon is a modern internet stock. So how about blue chips? Let's pick IBM. So let's do IBM with a student T. Let's retrieve this price series, look at the histo, and look at the plots that we have generated. The fit, well, not great, but seems to look okay, perhaps. And we see the tails are definitely flaky. So we still get conclusion that the student T isn't really all that great. But with the normal distribution, well, the fit is even worse, right? Look at this, we really don't get a fit. And the tail fit is even worse. It's pretty bad. At least here we see that green and orange are coming down towards the x-axis, and here with the normal disk, the difference is getting absolutely massive. So let's do a hypothesis test here as well. And here we only have 9 tests available, but still all 9 of them, 100%, are rejecting, right? We have rejected in all these messages, and we have all these p-values here at 0. So I would say, again, for conclusion, it's a pretty terrible fit, and the 5% hypothesis is rejected in all 9 tests. That's 100%. So we have the following dilemma. The student T is a good fit because the data is a good fit for the data because it does accept the jumps as part of its heavy tails, unlike the normal dist, which gives us bad fits. But mathematically, the student T cannot work with stochastic calculus, which requires that the distribution doesn't produce jumps. And equivalent to that is saying that the standard deviation converges quickly. And we also have to recognize that the normal distribution does, right? Whereas the standard T does not solve this jump problem. So what is needed is a better mathematical model than the stochastic calculus that we have. But nobody has found that yet. Absolutely nobody really was able to solve this dilemma. And therefore, unfortunately, for precision, and I'm emphasizing that this is not always the main objective, Monte-Carlo is probably the best that you can do. But Monte-Carlo can be slow, inefficient, and seems to be overkill for these standard options. So it is a real dilemma. One gives a better fit, the other one gives a not so good fit, but is in line with the theoretical assumptions. Monte-Carlo is in the end the only thing you can do, but it's inefficient. There we have C, and really nobody has found a way out of this dilemma. So I want to make another point here when we're talking about these parameters of descriptive statistics. They simply change over time. And pretty much everything of these parameters changes over time. The interest rate changes, the strength of the economy changes, exchange rate change, and keep in mind this exchange rates really represent the strength of the domestic economy, right? That's why exchange rates have to fluctuate, because it's the only way for different economies, different countries to adjust when it comes to their different economies' strengths. Management can change, regulatory and legal environments changes, public perception and reputation of a company changes, taxation changes, customer satisfaction, there can be lawsuits, and so forth. So it's a good idea to make the look-back period of a time series not too long. We can take any company today, let's just keep it with IBM, and we realize IBM today is not what IBM was in the 1940s or 50s, right? So things change over time. So we cannot take too much of a look-back period, but we would need a longer look-back period in order to have reliable parameters. So keep in mind time series behavior changes over time, and I emphasize at this point that you should be able to become friends with the fact that in descriptive statistics, time variant parameters are a reality, right? Parameters are not constant over decades. They change. And we have to recognize this when we do time series analysis, and above these numbers that we have computed and these plots that we've displayed simply are based on time series, and then we're deriving parameters that we assume are correct, right? So keep in mind these parameters change over time, and the appreciation rate A, for example, is a good example for that. That is all these assumptions that I've mentioned, from interest rate to a long list of items, right? And if you have a long-term portfolio management perspective and you're not interested in fast-paced option trading as the market makers do, then the appreciation rate A can indeed be used in a very proactive portfolio management manner. And in later sessions, we'll see that making the appreciation rate A time dependent is a very easy manner. And we can still use the Black-Scholes options framework for doing that. So making this time dependent is not a problem, not in terms of the theory, not in terms of the PDE, the partial differential equation, not in terms of the actual computations that we're going to do based on the Black-Scholes PDE. So time dependent is not a problem, right? But it has to be only time dependent. And I point out that value assessment is inherently subjective. And that's why it's also possible to make this part of the appreciation rate estimation, because everyone has different future expectations and everyone values value differently, right? Otherwise there would be no trade. And if you want to use the appreciation rate actively, then it's possible for you to find prices that you consider cheap or expensive and others do not, right? And that's really the key point to recognize, because value is a very individual assessment, right? If you prefer to keep your money, then you're not buying the asset. But if you really think this used car is worth more for me than the money I pay for it, then you would be a buyer because you'd like to convert your money into the car. And the other perspective, when you want to sell your car, then you say, well, for me it's more beneficial to convert this car into money again, into cash again, right? So if everyone had the same idea of value of something, then there would be no transactions. So value is inherently subjective, and we can, in later sessions, make this a proactive tool through the appreciation rate. I think this is important to recognize at this point, because there is simply so many factors that change over time and are being perceived differently over time. Here, look at this long list that we had. Okay, so to be complete and in line with what I say in my data sciences with Mathematica track, I also need to point out some data problems now. I had mentioned it in 2 previous sessions in the data science track. So, for example, you need to keep in mind that a blue chip company that may have been trading forever may show behaviors that you don't realize unless you look at the time series or look at some descriptive statistics about that time series. So for example, let's retrieve Ford from 1972. Mathematica has Ford since June 1972. And what we can easily see that is that apparently we have something of a valley on top of the mountain with a tall spike or tall pole that we have there. And not just with Ford, also IBM as a blue chip. Let's retrieve that time series and see if we see anything irregular in it. And again, we seem to be having a little bit of a valley on top of the mountain and a tall pole. How about GE? That's another blue chip. So with GE as well, we see that we have a valley on top of the mountain and a pole. Okay, so we have three blue chips with valleys on mountains and poles on the valleys. And the reason for that is simply that we have bad data. And that is because the long-term price series has been adjusted so many times for splits and dividends without high precision arithmetic that many of the sequential price series early in the series are identical. And if they're identical, that simply creates zero log returns. That's why you have these zeros here creating these values. So the reality was that the actual log prices of these differences in the 70s were not zero. So it's pretty much garbage data, because splits and dividend adjustments, if they're not done with high precision arithmetic, basically give you false prices. These prices, in particular the price changes, and that's what we're looking here when we look at the consecutive differences of the logarithm, then we're simply getting garbage data. So I summarize this as a couple of morals of the stories. So this is more a data science perspective, but you should adopt that when you're doing computational finance. Check your data. The data itself may be wrong. And inquire from the data provider what attributes the data has. So does the time series recognize splits properly? Is the data inflation adjusted? Is the data dividend adjusted? And was it concatenated from disparate or incompatible data sources? Is the data measured? Is it actual? Is it estimated? Is it sampled? Right? And what error do we have in the data? What are the error distributions that we have in the data? The data provider should provide that information. Is the data complete? Is the data missing? If it's missing data, then is the missingness interpolated? Is it imputed? If yes, what method was used? So all these things are necessary for a professional data provider to specify. There should be a data specification document. Next, you should always plot, display, or visualize your data. And some data problems are instantly visible, right? As you see here in these histors of these three blue chips. Of course, that doesn't mean you immediately have found the data, but you immediately know, well, something is probably wrong here. Then you should run statistical tests and not just the simple hypothesis testing that we did here. There are many more tests for statistical evaluation of the quality of a time series. For example, the Kolmogorov-Smirnov test, and there are several others. And this may point out to you errors that you may have in the data, and it may also point out mistakes you have in the distributional assumptions. Okay, I'm coming towards the end of this session. I want to put extra emphasis on some Mathematica features that I have used in this session that are worth extra mentioning. And one of them is evaluate in plots. So if you look closer at streamplot, we see that it uses Vx and Vy as inputs. So that's V with the first derivative with respect to x, and that is V with the first derivative with respect to y. We see that here, right, in the documentation. This gives us the three signatures that we have for streamplot. So we have V sub x and V sub y. And this gives us a streamplot of the vector field Vx, Vy of a function of x and y. So this is great. And it is because it is supposed to show us a visualization of the integral, right? Usually we'll have differential equations and we want to see what the integrated version looks like. We want to visualize the solution without having it, basically, because the result of the stream plot is a numerical approximation of the visual picture, of the visual dynamics, the flow that is represented by the differential equation in question. And if I now want to show the stream version of it, then there was no real differentiation in integration involved. But I need to provide them so that stream plot can do its job. I had to differentiate my functions so that stream plot can reintegrate it for me for the plot. So the first derivative of t with respect to t is 1. And the first derivative of e raised to the power of rt with respect to t is r times e raised to the power of rt. But if we can let Mathematica compute it for us with d, then we still have to put evaluate around it, because the way the plots work in Mathematica is that they sample the argument. This is important. They sample the argument pointwise. And this will take a very long time for complicated expressions, so we have to use evaluate around this expression. It's important that evaluate is, so to speak, the first thing that the plot function sees, and not just for stream plot. The same is true for plot or other plots like polar plot or list line plot and so forth. All right, have a look, not a loot, have a look at this plot again, which is the plot that we had at the beginning. You see these stream plots here. And note that I differentiated t with respect to t because I just want t on the x-axis, and I differentiated the exponential function of r times t. And now try plotting it after removing evaluate. Not a good idea. This is not a good idea because now stream plot has real problems sampling these expressions that we have. So keep in mind that we should use evaluate if we have the idea, or if we have the intuition that we are asking the plot function to plot us a very complicated expression here. It doesn't have to be a complicated function, but if it's a complicated expression, then it's a good idea to evaluate the expression first before we're passing it to the plot function. Okay, and next I want to point out something that I call interceptor variables, and this is just my own terminology. I'm not saying that anyone else is using it or that this is an official terminology. It's not. If you do a web search for interceptor variables, you're probably going to find nothing or something completely different, right? You probably won't find anything with it. I just call it this way because it is an effective way to intercept a computation in order to use the same thing later. So as we process lists, the kernel operates on them left to right. That means we can assign a variable to an expression when it occurs, and then use that variable directly in the same processing of the same row or line of that list. So in this example that I've used before, we store the result of square root of 2 times the inverse function in S in the second list element, right? You see that here, that's the second list element. And I store that in S because I then use S again, n of S. I use it again in the third argument, in the third list element. And I don't want to recompute it. Now in this case, it doesn't really matter because it's such a simple expression, it's such a simple computation and evaluation that it doesn't really matter. So for this one, it doesn't matter. But if it were a time-consuming computation or also a memory-consuming computation, we'd save a lot of time by assigning it to another symbol first before we use it. And we are really using it here when we are displaying the numeric value of it. It also makes your code more legible. It makes it shorter because n of s is shorter than n of this expression. Okay, so when we do this here, we store this expression in the second element, in the second list element, away in a variable that we use in the third element, left to right. Right? In the second we define it, in the third one we use it. And similar to this example that I showed you afterwards, here I stored two expressions in interceptors, S and S2. So here I use S2 in order to remember what I need later in S2. And also S gets an assignment here. And then here I use S again. I don't have to compute this expression again. And here I use S2 again, right? I find this very useful when you do this, because also this list expression now is used multiple times. In this case, 5 times. We're getting 5 rows of output. So I find this useful, especially when you have time-consuming computations or memory-intensive computations, or you're providing for a lot of rows in your output. Okay, the next one. I want to emphasize that parallelize doesn't evaluate its arguments. It leaves it in a symbolic nature, and it passes then these symbolic arguments to the subkernels in an unevaluated manner. So if you want to submit an instruction to create 10 million samples, right, and that means 10 million each to the 12 subkernels, then you're making your work much more efficient if you use parallelize on this first and you do a pre-processing this. So no samples are actually distributed, right? We don't want to submit 120 million samples from the master kernel to the subkernels. Imagine you did this. Imagine the master kernel would have to send 120 million samples to the subkernels. And then the question also arises, for what? We have already generated them. Now you're just sending the subkernels all these 120 million samples. What are you going to do with them, right? You want the samples at the end of the parallelism in the master kernel, right? So this is not a good idea. So the way to show this is that I'm giving you a timing comparison. In the following, no samples are ever sent to the subkernels. So here I use parallelize 12 times, and this took 2.3 seconds. And what happens here was that every of these 12 subkernels generated 10 million random numbers, right? There's 10 million on subkernel 1, 10 million on subkernel 2, 10 million on subkernel 3, and so forth. And this is much more efficient than if this expression were hypothetically evaluated. So let's force the evaluation, and then we're passing it out, and here only to 2, because this takes longer, so I'm only showing you this on 2 subkernels, and it takes over 6 seconds, right? So when we have this 6.06 by 2.36, this is about 2.5 times faster in the parallel version, and just on 2. So you really have to multiply this with 6, right? Because I'm talking about 2 out of 12 subkernels, right? So we have to multiply this with 6. So it's about 15 times faster, but it's also more efficient, memory efficient. The communication overhead is different. So keep in mind that you should try to parallelize with something that can be easily parallelized, and in this case it's just a list. Parallelize knows how to deal with lists, and here we have a list of 12 elements corresponding to these 12 subkernels that we are now submitting to the 12 subkernels that I have. Okay, so try to make use of the fact that we don't want to pre-evaluate stuff that should really be evaluated on the subkernels. All right, so here in conclusion, in the first example, we generate 120 million samples, 10 million on each subkernels, but on each subkernel, right? We're not generating them and pass them to each subkernel. They're not generated for each subkernel, but they're generated on each subkernel. None were generated in the master kernel or distributed to them. And in the second example, we generated 20 million samples and then sent them to only 2 subkernels, and it took 2 to 3 times as long. Yes, 2.35 times as long. So, conclusion, why generate them in the master kernel in the first place? All right. So, next I would recommend that you get familiar with callout, because you can really enhance the meaningfulness of your plots significantly. A callout can accept pretty much any expression to display, and you can position it anywhere on the plot, pretty much anywhere you want. And I also recommend you get familiar with compilation. We have bytecode compilation as well as C compilation, right? Speed up your computations to a machine code level. Very useful in many cases. And I should add that over time the compiler is getting better and better and better. We already got a pretty good compiler improvement in version 8, and we now have version 2 and 12, we now have version 12 with 12.1 in beta testing. So I know from experience from the last 4 integer version number, the compiler in Mathematica, including the C compiler, is getting better and better. You really get a lot of bang for the buck if you use C compilation. Next, I recommend you get familiar with CUDA itself and with the CUDA link package, and also with library link to call CUDA from a Mathematica session. It's library link that opens you a world of possibilities. You can significantly improve your coding if you understand proper parallelization of the subproblems. And GPUs are essential for future technologies such as artificial intelligence, machine learning, and deep learning. So I think pretty much anything scientific that needs massive parallelization is a candidate for GPUs, the CUDA link package for compilation, and I think you should really get familiar with it. It's not that hard for a C programmer. And in this group, I also want to include the practitioners in financial options who need to quote financial options on a massive scale. They're called the market makers, as well as researchers of any kind. I think eventually CUDA will really make your life much better. And again, CUDA itself is important, the CUDA link package is important, and together with compilation and together with library link, you will have a wonderful experience. And note, the CUDA package doesn't work right on Linux, but you can make it work. And I have posted an answer on Mathematica Stack Exchange that gives you more details on how to make it work on Linux. See this example of mine that I have on Stack Exchange. Okay, that brings me to my final comments for this session. Please also have a look at my parallel track about data science and Mathematica. The playlist for sessions 1 through 11 are here at this link. And the playlist for sessions 12 and after is here at this link. These are 2 playlists for that. And I also want to point out more explanations of exploitation of symmetry and integration I have in session 8, starting about at 7:41. Here is the link. And I've used some parallelism features in this session, and I go deeper into parallelism in my 12th session of the data science in Mathematica track. And I'm giving you the link here. If you want to learn about parallelism in Mathematica, have a look at this one. I was barely able to touch on this. Parallelism is not the main focus for this particular session here. This was just an introduction into financial option theory with Mathematica. So my next session in the data science with Mathematica track will be about the use of CUDA and the CUDA link package in the Mathematica environment. It's not there yet. It's gonna be my session number 13. Stay tuned. On my other track, please have a look at the data science track as well, where I specifically focus on harnessing the Mathematica system on data science, which is largely relevant for practitioners in the field of option pricing theory. All right, this is the end of this session. I hope I see you in session 2 of this new track, and I hope I see you in the data science track. Thank you. Bye-bye.